most amazing feature of a capacitive sensor is its ability to sense through a completely shielded housing. Capacitive sensor works by detecting the change of capacitance due to the influence of external objects. Roughly speaking, capacitive sensor comprises of electronic circuits that measure capacitance across electrodes, also known as antennas. When the capacitance changes, the circuit and the algorithm infer the presence of an external object. But exactly where is the capacitor, and how does a human finger change the capacitance? A common model is that the electrode forms one plate of the capacitor, and the grounded finger forms the other plates and changes the overall capacitance of the sensor. But our experience is that users need not be electrically connected to the circuit or put their feet on the ground to operate the sensor. So grounded finger as a requirement for capacitive sensor is a misconception. So let's look at the physics on how an ungrounded object influences capacitance. When conductors are connected to the source, the electric field from the source pushes the charges out to the conductors. The positive charge and the negative charge are attractive, so they move to each other as close as possible. Charges on the same plates are repulsive, so they push each other away to the edges. As more charges join the plate, they build up electric field to oppose others from joining in. Eventually, the net force along the conductor is zero and the charges stay in equilibrium. This is when the plates have the same potential difference as the voltage source. And the capacitance is defined as the ability to store charges on a per volt basis. When an external conductor is put nearby, it cuts into the electric field. The electric field polarizes the conductor and energy is transferred to the polarized charges. The polarized charges get energy from the plates and the plates now have a lower potential. If the source is still connected, more charges will join in the plates until the plate's potential is back again. The external object allows more charges to store in the plates and therefore it increases the capacitance. So even when the external object is not physically connected to any of the plates, it is still capable of influencing the capacitance. Any charge in the system is subject to attractive forces from the unlight charges and repulsive forces from the light charges. This complex tug of war happens to every single charge in the system. Based on this, a mathematical model can be developed to solve for the charge distribution which would satisfy the equilibrium condition as mentioned previously. The charge distribution shows the physics in the system and can be used to calculate the capacitance. For a coplanar capacitor, numerical solution shows that the capacitance increases when the third plate is placed nearby. And the third plate is indeed polarized by the electric field. Two plates are required to detect a nearby object. This dismisses the idea that CapSense uses one plate to detect the object's capacitance with respect to infinity. We can also do numerical experiments to study the effects of antennas geometry on the sensitivity to external influence. For a human touching the antenna configurations as shown, the capacitance increased by 0.056 picofarad, amounts to 30% increase. If the antennas are enlarged, they can pick up more influence. The capacitance change is more, and the percentage change is more too. So larger antennas are easier for the measuring circuits. If the distance between the antennas are shortened, the electric field are more confined. Although the capacitance is higher, the delta change is actually less and make it a less effective sensor. In most designs, one antenna is made as a touch focus point and the other integrated to the ground plane. Without special care, the ground plane can pick up the object's influence as well. So how can we increase the sensitivity of one plate and reduce the sensitivity of the other? One method is to make one antenna more accessible than the other. Another method is to control the size of the antenna and will be explained here. In a simulation of a finger 2 mm above a coplanar structure, the capacitance increased by 12%. When the human body is included in the calculation, the capacitance increased by 22%. The human body itself doubled the influence on the capacitance. The body by its huge surface area and the finger by its close proximity couple themselves to the antennas. If one of the plates is enlarged to provide good and constant coupling to the human body, then the finger approaching the smaller plates becomes the deciding factor for the change of capacitance. Using numerical simulation for the above configuration, we see capacitance change by more than 100%. If the finger approaches the big plates, it doesn't close the loop and the capacitance change is minimal. So by having a large ground plane, which is one of the antennas, the sensitivity automatically goes to the smaller antenna, which is meant to be the touch focus point. Even if the ground plane is made smaller and the touch antenna made bigger, the sensitivity still follows the smaller plates. The smaller antenna gets more sensitivity because of the higher percentage of change compared to the bigger antenna in the same configuration. But the smaller antenna do not necessarily get more absolute delta C than a bigger but less sensitive antenna in another configuration. So to enjoy higher sensitivity from a higher percentage change of a smaller antenna, the sensing IC must have a good signal-to-noise ratio to begin with. If a capacitive sensor is connected to the mains wiring, effectively, one of the plate's area is increased significantly. The absolute delta C and therefore the signal level is higher. The touch antenna, because of its relatively small area, will get all the sensitivity. The mains wire, because of its relatively big coupling area, will become insensitive. Without the inverse relationship, the mains wire will get a lot of false triggers. Thank you for watching and I hope you enjoy the video.